Welcome to AP Chemistry at Hononegah High School. I'm Brian Brown, and today we'll be doing some equilibrium problems. So we're going to look at the questions in the equilibrium practice worksheet that I gave you. Now the first reaction is a decomposition of SO2Cl2. Notice it says it's a highly reactive compound, and when heated it decomposes. And it says this decomposition is endothermic. So one of the things I want to note right away before we jump into the problem is what that means. Well, if it's endothermic, that means energy is on the reactant side, and we have to add energy to react with SO2, Cl2 to make those products. So that's something that may be useful later on. So I want to notice that right away. Second thing I notice is it gives us the mass. It says we have 3.509 grams of SO2, Cl2. Now, right away, if you recall from the different problems we looked at, whenever we've had masses in this chapter, we've always converted them to moles because in a Kc problem, you need molarity. Well, moles divided by liters is molarity. And in a Kp problem, we need pressures. Well, we use moles in PV equals nRT to get a volume of a certain number of moles of gas at a given temperature to figure out what its pressure is. So right up front here, we're going to go ahead and calculate how many moles we've got. So I know the molar mass of this substance is 135.1 grams per every 1 mole. So when we do the calculation here, we end up with 0.025973 moles. So we know up front that's how many moles of this substance we have before anything occurs. So this is pre-equilibrium. So under initial conditions, we've got that many moles of our reactant. Last thing I want to process here is the delta N, which we've talked about from time to time. Now we've got a gas system here, and that means our number of moles of gases may be changing. And delta N may be a useful number if we're going to convert between Kc and Kp. So notice on the product side, we have one SO2 and one Cl2. That's a total of 2 moles of gases. And on the reactant side, we just have one of our SO2Cl2s. So our delta N for this reaction is a positive 1. So before we looked at anything, those are actually three ideas I notice in the given information that may be useful later on. So at this point, we're ready to jump in the problem. So A says if the Kc for this reaction is at 650, well, right away I notice that's a different temperature. So that means we're probably not going to be dealing with the masses and the temperatures that we dealt with before. So this is a side question. So we're at 650 K, and it says the Kc is 0.045, and it wants to know what the Kp is. Well, if you recall the Kp expression, Kp equals Kc times RT, and we need to use our atmosphere version of R, and we need to use Kelvin temperature, to the delta N. Well, we were given the Kc, and we just calculated this delta N was a +1. So fundamentally, that must mean that Kc times RT will equal our Kp. So if we just multiply this out, make sure I get the right numbers here. The Kc is 0.045. Our R value is 0.0821, and that's the liter atmospheres over mole Kelvin. And finally, our temperature in Kelvin is given as 650. So when we multiply this out, we end up with, to 2 sig figs because of that 0.045 and the 650 K, we end up with a K value of 2.4. So we know at that temperature, if that's our Kc, that's what the Kp would be. So that's how you answer A. B goes on to say, went a little too far there, what is the Kp of the reverse reaction? Well, same temperature, so we know we're dealing with the same situation we had before, Kc of 0.045, Kp of 2.4. And we're reversing the reaction. Now you got to be careful, do not confuse this with what we talked about back when we looked at Hess's law. That's where we're looking at when we reverse, we change the side that energy's on, so we switch the sign of the delta H. Well, that's not what we're looking at here. When we talked about a reaction where we knew what the forward reactions K was, and we wanted to know the reverse, the two are the reciprocal of each other. So if I want to know what the reverse is, it's going to be the reciprocal of the forward. Well, we just calculated the forward reaction was 2.4, so 1 over 2.4 should give us the K of the reverse. And that's going to end up being 0.42 to 2 sig figs. So that would be the Kp for that reaction. So remember, if they were asking me what's the Kc of that reaction, I'd take the reciprocal of 0.045 because those are the K values, the respective K values at that temperature. Next one, C. says, what would be the pressure in atmospheres if the bulb, in the bulb if no dissociation of SO2, Cl2 had occurred? So we're back to talking about our reaction and conditions listed here. So we're back to talking about our 3.509 grams of SO2, Cl2, and we're putting it inside the container, and at time zero, none of it's decomposed. What would our pressure be? Well, remember right here, we just calculated, because I said it might be useful, the number of moles. So when we think it through, if we know that PV equals nRT, and we want to know pressure, that would equal nRT over V. And N, R, T, and V are all known quantities, so all we have to do is plug them into the equation. So the trick you need to get here is what we're really talking about is initial conditions. And initial conditions, we often have to get our data in appropriate units. KPs, that's pressures. KCs, that's concentration. Here they're talking about pressures, so we know we're looking at PV equals nRT. So all we have to do is plug in our number. It was 0.02593, and that was moles. And then we had our R value, same one we're going to use, 0.0821. And didn't write it before, but remember that's the liter atmosphere over mole Kelvin. And we multiply that by our temperature, which our temperature under initial conditions was 375 K. And that is all divided by the volume of the container, which was a 1.00 liter container. So when we plug in our numbers and round to 3 sig figs, we end up with 0.800 atmospheres. So those would be, or that would be what the pressure is inside that container at time zero. Because at time zero, all we have is the reactant, which hasn't decomposed yet. Which brings us to question D. When the system has come to equilibrium, so now we know we're talking about a system where we had initial conditions and it's becoming equilibrium, this is where we get into icebox. And with icebox, first thing we do is we always start by writing our reactions. So we had SO2, Cl2, and that was undergoing a double replacement reaction to decompose into SO2 and Cl2. Now, the quick way to set up our icebox is use that in our heading. So we're just going to write the ICE right underneath it. And I'm going to make it pretty here by making an actual box so we can keep our data separate from each other. So we keep everything organized. And remember, we just use our balanced equation as our headings for our icebox. Now, in the previous problem, we just figured out that our initial pressure was 0.800 atms of SO2Cl2. Now this is before any decomposition happens, so we know those both are going to be zeros. Now next, to get C for this, we look at, well, how is this going to change? Well, it's a 1-to-1-to-1 stoichiometry, and we have all reactants, so we know our reactant concentration is going to go down, so it's going to be minus. We just don't know how much exactly it's going to go down, so we're going to call that minus X. But because of the 1-to-1-to-1 stoichiometry, we know our products are both going to be plus X, which means I plus C gives us our equilibrium condition. So that means 0.800 minus X would have to represent our pressure of SO2Cl2 at equilibrium. SO2 would equal X and Cl2 would equal X. Now at this point, we'd normally set up our Kc or Kp, Kp in this case, of course, we're dealing with pressures, equilibrium expression, and they would have given us probably what the Kp was and so forth, and we would have moved on. But you'll notice right here, they gave us something that makes this a ton simpler. It said the total pressure is 1.43 atmospheres at equilibrium. Well, I know I have 3 gases in there at equilibrium, and I know they have to add up to 1.43. And I know my first gas would be represented by that pressure. My second gas would be X, and my third gas would be X, and that has to all add up to 1.43 atms. So I've got a simple algebra problem. 0.800 minus X plus X, X is cancel. So I have 0.800 plus X equals 1.43. X is going to equal 1.43 minus 0.800. So that means X is going to equal, because it has to, 0.63 atms. And at this point, I can plug that in for my X's here, because that's what that X represents, is the pressure at equilibrium. And I can actually then calculate my SO2, my Cl2, and my SO2Cl2. So the first one, SO2Cl2, well, remember it's 0.800 minus X, and X was 0.63. So that's going to equal 0.17 atms. And then my other two gases, SO2 and Cl2, both of those were X. So their partial pressures are going to equal each other, and that would equal the value of X, which was the 0.63 atms. And now we know the partial pressures of all three gases at equilibrium. So because they gave us the total pressure, and we knew the pressures at equilibrium with respect to X, we can add up and get the total. Quick, easy way to solve for X. Now that brings us to E. Now notice it says find Kp for the decomposition. So in order to find Kp, we need an equilibrium expression. And the type of K we need is Kp because that's what it's asking for. So we need to write the Kp expression. Well, the Kp expression would equal the products raised to the power of their coefficients, which in this case would be SO2. So we need the pressure of SO2 raised to the power of its coefficient, which was the first. We need the pressure of Cl2 raised to the power of coefficient. So that was A1 as well, all over the pressure of our reactant, which was SO2Cl2, raised to the power of its coefficient, which was a 1. So if we knew those concentrations, we could plug in raised to their respective powers, and we would calculate the Kp. Well, that's what we just did in the previous problem. We knew the top two pressures were both 0.63, and we knew the pressure of the SO2Cl was 0.17. So that means 0.17 on the bottom. Plug it in our calculator, round to 2 sig figs, and we get 2.3. So that has to be our Kp at equilibrium at this temperature, 600 or 375 K. So we already had the pressures at equilibrium calculated. All we had to do was plug into the expression. And that brings us to F. At 375 K, the pressure of SO2Cl2 is 0.24, SO2 is 0.55, and Cl2 is 0.68. So they're giving us our pressures. Now the question is, are we at equilibrium? Well, remember, the Kp expression under non-equilibrium conditions, we actually call the Q. So the Kp expression, it's really the same as the Q expression. But since we don't know if it's at equilibrium or not, we can't call it K. So it's going to equal the same thing. It's going to be the pressure of the SO2 times the pressure of the Cl2 over the pressure of SO2Cl2. Plug in our numbers into that, and we're going to get what is called Q. So our reaction coefficient, but not necessarily at equilibrium. Now remember, what we're really doing here when we plug in our numbers, which it said, let's see, 0.55 was SO2, Cl2 was 0.68, and SO2Cl2, that was the 0.24. When we actually plug those in and calculate, we get 1.6. Now that does not equal what we had before. So 2.3, 1.6, not the same numbers. So that means we are not at equilibrium. So are we at equilibrium? No, we are not at equilibrium. Because the only way we're at equilibrium is if these concentrations plugged into the expression return the same value of 2.3. And since it doesn't, we know we're not at equilibrium. So the next second part of this question is, if not, which direction will the reaction proceed to reach equilibrium? In order to answer that, you have to really think about what it means when our Q is smaller than K. So really, the way books talk about this is we would say Q is less than K. What does that mean? Well, the reaction or the K expression, equilibrium expression, is products over reactants. So if Q is smaller than K, that would mean the number on the bottom, reactants, was too big, and the number on top, products, was too small. That would give us a smaller value than K returned. So that must be what's happening here. So if we know our reactants are too big, that means as this reaction progresses, our forward rate, which is too many reactants, so we got a higher forward rate than the reverse rate, is going to dominate. So as time goes by, our products are going to go up and our reactants are going to go down until we reach equilibrium. Well, that means we're going to favor the production of products, which means we're going to be shifting equilibrium to the right. So because the Q is less than K, your book would say that means equilibrium is going to shift, or I should say, we're going to shift the reaction to the right to achieve equilibrium. And all that really means is our product concentrations are going to go up and our reactant concentrations are going to go down. That's why we call it a shift to the right, because we're favoring the production of products. Now, is there another quicker way to do this that we talked about? Yes. Remember I said, if you look at it in alphabetical order, there's a shortcut to this. So if Q is less than K, that means K is greater than Q. Remember, our greater than or less than sign becomes an arrow, and notice it points to the right. So if you look at is how does K compare to Q, you can always see whether it's shifting right or shifting left to achieve equilibrium. Now, that doesn't mean you understand what's going on, so I wanted to look at that first before we looked at the shortcut. Next one, G. If the temperature were raised to 500 K, what effect would this have on the equilibrium constant? Explain briefly. Now we have to go back to our original equation and notice something that we said from the very beginning. It says the decomposition endothermic, that means energy is on the reactant side. Now, remember, if we increase the temperature of this system, we're going to increase both the forward and the reverse rate. That's right out of last chapter where we talked about reaction rates and the effect of temperature on them. But that doesn't mean they increase at the same rate. And that's where what the endothermic versus the exothermic direction is becomes very important, because the forward reaction was the endothermic direction. Remember, the endothermic reaction needs energy. So really what's going to happen here is the forward rate is going to increase faster than the reverse rate is going to increase. And we're going to be left with a situation where we're not at equilibrium when we increase the temperature. So what you need to understand here is that's going to favor the production of products. Well, if you go back to our original K expression, remember it's products over reactants. So if we're favoring the production of products to get to equilibrium, we know we're going to have greater product concentrations and pressures than we had before, and lower reactant pressures and concentrations when we reach equilibrium. And that means our K is going to get larger. So that's the sequence of events you need to understand here to answer this question. What it really says, or if you break it down, since the forward reaction is the endothermic reaction, increasing temperature is going to favor the production of products at equilibrium, and therefore K is going to increase. So it's going to increase the value of K. Remember, temperature is the only thing that we looked at that is going to have an effect on the actual value of K. So in this particular case, we know the forward reaction is endothermic. That's going to favor the production of more products at equilibrium, and that means our value of K is going to increase. And remember, we're increasing both directions, but the endothermic direction is going to increase in rate more. And in this case, that's going to favor the production of products.